So this is the fourth and final question on normal distribution. What's interesting about this one is that there is a combination of distributions, and you will see a little bit later. So let's just read the question. The weights of chickens for sale in SOP are normally distributed with a mean of 2.5 kilograms. So that would be our mean, the 2.5 kilograms. And then the standard deviation 0.3, that's going to be a standard deviation, or otherwise we can define a continuous random variable W that corresponds to the weight of the chickens that follows the normal distribution with a mean of 2.5 and the standard deviation of 0.3, and we have to square it, don't forget that. Find the probability that weighs less than 2 kilograms, so you want the probability that W less than 2, and we will calculate all of those very quickly on the calculator on the left. Find the probability that weighs more than 2.8. Both of those are going to be similar processes. In the diagram below, say the areas that represent the probabilities from 1 and 2, and then finally find the probability that it weighs between 2 kilograms and 2.8 kilograms. So let's start with number 1. We have menu, and then probability, and then distributions, and then normal CDF, because we want less than, more than. For the first one, the lower boundary, it's okay to approximate the negative infinity. That would go up to 2. The mean is 2.5, and the standard deviation is 0.3. And that will provide us with the answer for the first question. Now if we round it straight away to save a bit of time, it's going to be the 0.0478, right? 0.0478 to 3 significant figures, and that would be an approximation here. Right, now we want for bigger than 2.8, so I'm going to copy the same characteristics, but instead of smaller than 2, I will make it bigger than 2.8. So the lower boundary here would become 2.8, and then the upper boundary would become any really big number, and then the answer is going to become 0.159. rounded to 3 significant figures, 0.159. In the diagram below, shade these areas to represent the probabilities. The one is smaller than 2. I can see the mean, which is the 2.5 kilograms. One standard deviation is 0.3, so I can sort of count in standard deviation, so that will be more or less the first standard deviation. So it's going to become 2.2, right? And then the second standard deviation is going to become just a 2. Here we go. So that would be the probability here that represents that part, and then you could kind of like more or less size up whereabouts the 2.8 is going to be, but let's just put it somewhere here, 2.8, because we know it's going to be above the mean, and that's going to be the diagram. Okay, find the probability that weighs between 2 and 2.8. I can use the same CDF above, perhaps there's other reasons too, but that's already easy enough. Between 2 and 2.8, mean and standard deviation will not change, of course, 2.8, and then that would provide me with the probability, which is, so let's write it here, the probability of between 2.2 and 2.8, and that's equal to 0.794 to 3 significant figures. Again, that's an approximation. Now the interesting part is the second part, because suddenly the scenario is changing. So a customer buys 10 chickens. Find the probability that all chickens weigh between 2 and 2.8 kilograms. Now the way you have to think about it is the probability for the first one to weigh between 2 and 2.8, right? So it's either weight between the given weight or not weight. That's another way of kind of like thinking about it. Either ways or no ways, right? And we know that the probability is going to be 0.794, and then again it's either going to weigh or it's not going to weigh, right? So another 0.794. So if you consider what's the probability of all of those, or wait, basically it's not about the probability of all of those, it's about like trying to identify that suddenly, apart from having calculated the probabilities through a normal distribution, what I have in front of me right now is essentially a binomial distribution, because each choice, right, 9-4, each choice is independent from one another, right? You just choose chickens out of the sort of kind of like, that they are for sale, out of a large group of chickens, and every time you pull a chicken out, it's either going to weigh with a chance of 0.794, or it's not going to weigh between 2 and 2.8 kilograms with a chance of 1 minus 0.794, and I can calculate that and I can give it a specific price, which, let's don't be lazy, let's just do that. 0.794, what's that? So that's going to be the 0.206, and that's going to be the probability of failure, because the 0.794 is going to be the probability of success. So if I define as x a variable, right, that corresponds to the number of chickens weigh between 2.2 and 2 point, what was that? Let me just not confuse with the W now. Number of chickens weigh between 2 and 2.8 kilograms, then that variable follows the binomial distribution with the number of trials to be 10 and the probability of success to be the 0.7935. We could have used this 0.794, but we're not going to use that number because that has been rounded, so you're going to use what the calculator gave us, the 0.793554, right? That's going to be way much more accurate, right? And then what I want to find the probability that all 10 of them are weighing between 2 and 2.8, so that will be the 0.793554. Let me just move this a little bit so you see what I'm writing there, to the power of 10. And then binomial distribution, you go back into your calculator, you go into another probability, and then another probability distribution, and then you have the binomial PDF here. Then we're going to have to give the number of trials, which is 10, the probability of success, which is the 793,554, and then the value, I want all 10 of them to weigh that. Press OK, that's going to give you 0.206, which I'm not so sure it's quite correct, because that did a different calculation. I had a different calculation there. So let's just go there, back into probability, and then distributions, and then here number of trials we have 10, and then probability of success point again 793,554. So much for making a quicker video, right? I made a mistake and I have to go back, but that's okay. You know how that works. I'm sure everybody's doing mistakes, so press OK. That's going to give you the 0.09903, which is the correct answer. So 0.09903, right? or 0.00990 to three significant figures, which is the correct rounding. Finally, for the last question, you're going to need the normal PDF, the normal CDF, I'm sorry, not the PDF, because we want for bigger than 7. So menu, and then probability, and then distributions, and then we're going to have to go all the way down the end. Where's the normal? When go a little bit more careful, PDF, that's what I want, the normal CDF. Twice I ended up with the inverse normal binomial. With the inverse binomial, we don't want that. We want the CDF. Number of trials, we have 10. Probability of success is the 0.793, and then 554, and then the lower boundary, of course, is going to be 0, like none of the chickens were in that. And then the upper boundary, it's going to be no, that's a mistake. We want either 7 or above, so the lower boundary is going to be 7. Hey, this question. And the upper boundary is going to be 10. Press tab, press OK. 0.867, 0.867, and that's going to be to three significant figures. And then again, I've neglected writing what's on the calculator screen, so let me just emphasize that, because you need that to put it down as you're working. So 10, 0.793554, 7, 10, and then the result is right above it. That was a good exercise that starts as a binomial, as a normal distribution that develops then into a binomial distribution. Very, very good exercise. Perhaps you should attempt to do it again on your own and try to do less mistakes than I did myself.